We are now starting on kinematics. This is often what a lot of people think of as the first part of physics. A lot of people start off with kinematics when they do physics. If you've taken physics in high school, you probably started off with kinematics. That might be the only thing you remember from physics in high school, and that's okay. We will be discussing kinematics now because I wanted to talk about vectors and units before this. I'm going to this is the chapter 2 kinematics slides that we'll be going over right now. Just before the break, we talked about acceleration being the rate of change of velocity with respect to time. We can also think about that as being a change in velocity over a change in time. That's going to be the case if acceleration is constant, which, okay, to a first approximation, that's usually true. Most of the problems that we're going to deal with will have a constant acceleration. We've also said that the velocity is equal to the rate of change of the position with respect to time, but we can also, alternatively, say perhaps the change in position over the change in time is equal to the velocity. Now, that is only true if both acceleration and velocity are constant. That gets some pretty boring problems. If the acceleration and the velocity are constant in a problem, the problem is remarkably dull. And so it'll be very rare that we have problems where that's true. And so I can say delta x over delta t is equal to the velocity, but that's only when the acceleration and velocity are constant, which is a boring problem. You can always say that the instantaneous velocity is equal to the derivative of x with respect to t. That part is always true. The first 2/3 of this is always true. It's just this last little bit on both of them that's only true if certain things are constant. So be careful about that. Got this example of motion. A 50-gram ball traveling right at 25 meters per second bounces off a brick wall and rebounds at 22 meters per second. A high-speed camera records the event and shows that the collision lasted 3.5 ms. Well, remember last time when I said y'all need to memorize the SI unit prefixes and all that? Well, this is where that's going to come in handy. You can just look at ms and say, oh, that's milliseconds, and milli is 10 to the -3. I really want you to, if not memorize it, become very, very familiar with it so that you can very quickly say, okay, yeah, milliseconds, that is 10 to the -3, so this is 3.5 times 10 to the -3 seconds. So question, what is the acceleration of the ball during that collision? Let's assume that the acceleration is constant. If the acceleration is constant, then we can use this equation. Acceleration is equal to the change in velocity over the change in time. I want you to take, let's say a couple minutes to try this out on your own, do this calculation on your own, find the change in velocity, divide by the change in time, find the acceleration. Be very careful when you're looking at these velocities and remembering velocity has a direction to it. So think about that and think about how to deal with direction. And the prompt was, we've got a wall. Here's our wall like that. And we've got a ball that comes in at 25 meters per second, and then it bounces off at 22 meters per second. Now pretend that I don't have any weird angles like that. Just pretend that it goes straight back like that. That'll make it a lot simpler if there's no change in angle there. And I said that acceleration is change in velocity over change in time. Well, what is change in velocity? One thing we're going to learn this semester is that the change in velocity, the change in anything, is going to be the final minus the initial. So the change in a velocity is the final velocity minus the initial velocity. The change in a position is the final position minus the initial position. The change in your bank account is your final bank account minus your initial bank account. We can apply that delta. This triangle is a delta, and that just means change in. Delta means change in. And that's over the change in time. So that's going to be t final minus t initial, but we don't actually know when any of this happens. We just know that it takes 3.5 milliseconds. Well, final velocity. What is my final velocity of this ball? Well, remember, it comes in this way and it leaves this way. I'm going to say that this is a positive velocity because it's going to the right. I'm going to say that that's a negative velocity because it's going to the left. My final velocity has to be negative. It's going to be negative 22 meters per second minus positive 25. Minus positive 25. All divided by the change in time. I don't know exactly when it started, but I do know that it took 3.5 milliseconds. If something starts on a Tuesday and takes 1 day, it's going to end on a Wednesday. If something starts on Thursday and it takes 1 day, it's going to end on a Friday. So it doesn't matter when it began, it just matters how long that it was. So it doesn't matter when this began, it just matters that how long it is, which is 3.5 times 10 to the negative 3 seconds. I can get my calculator. Fun fact, this calculator I bought right before my first day of 10th grade, meaning that I bought this in 1999. And so this calculator is actually older than most of you. So take that for what you will. Okay, negative 22 minus 25. Oh, by the way, what is that going to be? Negative 47. We've got a big negative number divided by 3.5 times 10 to the negative 3. That's going to get us negative 13,430-ish. And what are the units? Well, the units of these up here are both meters per second, because that's the velocity. Down here it's seconds. So meters per second, divide that by seconds, you get the meters, and then per second squared. I've got 2 sets of seconds in the denominators. So meters per second squared, which is exactly what you'd expect from an acceleration like that. Yeah, we get negative 13,430 meters per second squared. That's quite a bit. It's because it took a very, very short amount of time for this to happen. If you have a very short amount of time down there, then, well, it's going to be a very large acceleration. I do have that negative there, and so that means that it had to go from going forward to going backwards. It shed all of its forward velocity and traded that for a huge amount of negative velocity. And so giving up all of your positive and getting a whole bunch of negative, that'd be like giving up your whole bank account and getting into huge debt, which absolutely none of you have any experience with, obviously. That's a joke. So you would have this big negative number being attached to whatever happens to your bank account if we're talking about money this way. Why is this delta t in the denominator? Why is that 3.5 times 10 to the negative 3 instead of just 3.5? That's because it took 3.5 ms, and ms stands for milliseconds. Milliseconds, 3.5 milliseconds, is the same as 3.5 times 10 to the negative 3 seconds. We always need to convert everything that we've got into seconds. I'll write this down here. convert everything into seconds and into kilograms and into meters. If you convert everything into seconds, kilograms, and meters, everything is going to be fine. This looks weird. Okay, I've got a base unit, seconds. That's a base unit of something, of time. I've got a base unit of distance right there. Meters are a base unit of distance. Then I've got this one weird outlier. Kilograms? Grams would be the base unit, but I wrote down kilograms. I don't know why we do it this way. It would make a whole lot more sense to convert everything to seconds, grams, and meters. But because of the way that we've set everything up, we have to make it kilograms instead of grams. But always remember this, convert everything into seconds, kilograms, and meters. We solved this question. We got 13,400-ish meters per second squared to the left. And the hints that we need, convert grams to kilograms. Actually, did that ever even come up? Did we ever need to convert grams to kilograms for this? No. If this ball was 50 grams, it would have had that same acceleration. If it was 5,000 kilograms, it would have had that same acceleration, because acceleration just cares about your change in velocity. That is all we need to care about for this. So you don't have to care about the mass for this kind of question. However, it is always a good idea to convert grams to kilograms. Get in the habit of converting grams to kilograms, converting milliseconds to seconds, things like that. And get in the habit of saying right is positive and left is negative, and forward is positive and backwards is negative, etc., etc. Why is the mass not important? That's an excellent question. That's because the acceleration does not care at all about mass. And you can think about that in terms of a, let's say a sports car and a motorcycle. If you have a sports car and a motorcycle, they can, let's say they can both accelerate at the same rate. They have very different masses, but let's say that we picked out a particular motorcycle and a particular sports car that could both accelerate from 0 to 60 miles per hour in the same amount of time. Well, then they could have the same acceleration. If you're changing your velocity by a certain amount, 0 to 60, in the same amount of time, let's say, 8 seconds. I don't know what's a good acceleration. 0 to 60 in 8 seconds. We're not going to go crazy here. You can figure out the exact acceleration from that. It's going to be delta V, final minus initial. Your final speed is 60. Your initial speed is 0, divided by delta T, 8 seconds, whatever it is. Convert it all to meters per second and things like that. And suddenly you have an acceleration. Now, the sports car is going to have a lot higher of a mass than the motorcycle. And that doesn't matter. The mass of the motorcycle versus the mass of the sports car does not change how quickly they can get from 0 to 60. I'm going to write down a random polynomial. And that random polynomial is x is equal to beta t, that's the letter beta in Greek, plus 1/2, I'm just making up something, times gamma, that it looks like a y with an extra little curl on it, times t squared. So I wrote down this polynomial like that. What can we do with this polynomial? Let's take the derivative. As I've said before, the derivative of x with respect to t is equal to the velocity. So take the derivative of this. Take the derivative of this with respect to t. Well, that's dx dt, and that's equal to v. So I can say that v, I'm just taking the derivative of this stuff with respect to time. So derivative of that with respect to time, as I said here, that's equal to v. Derivative of this with respect to time, that's just beta, plus derivative of this with respect to time, let's see, that 2 comes down, it becomes 2 over 2. That's 1 times gamma times t, so plus gamma t. So if I took the derivative of this, I would find that the velocity is equal to beta plus gamma t. Well, now let me take the derivative of this. If I take the derivative of that, I remember we said that the derivative of velocity with respect to time is equal to acceleration. So if I take the derivative of this, and this, take the derivative of that with respect to t, I get acceleration is equal to, well, that's a constant. So if I take the derivative of a constant, that goes to 0, plus gamma times t. If I take the derivative of this with respect to t, I just get gamma. That means that this entire time, my gamma there was actually the same as my acceleration. I can now go back and replace my gammas with acceleration. That means that this right here, we'll do this one, velocity is equal to beta plus acceleration times time. Let's look at this. Okay, my velocity is equal to something plus my acceleration times how long I'm accelerating. Acceleration is my change in velocity over time. It's how much my velocity has changed in a certain amount of time. Well, if that's my change in velocity over time, and that's time, this term right here is pretty much just my change in velocity. So that's kind of my final velocity right there. That's the velocity that I'm looking at. My velocity is equal to something plus my change in velocity. The only thing that makes sense that would go in there would be my initial velocity. This is my final velocity. It's supposed to be an f right there. So this is v sub f. Velocity final is equal to velocity initial plus acceleration times time. Velocity final is equal to velocity initial plus acceleration times time. That's a valid equation. This is a true equation as long as the acceleration is constant, and it usually will be in this class. And we've shown that this entire time, beta has actually been initial velocity. And we already had that gamma this whole time had been acceleration. Therefore, I can rewrite this equation as x is equal to v initial times t plus 1/2 times a times t squared. We have discovered one of the kinematics equations that we'll be using a lot this semester. I show all of that. Oh, I do have a question. Oh, is this in the formula sheet? I need to post the formula sheet. Yes, the formulas that I go over in class will generally be on the formula sheet. The formulas that are usable in many situations will be on the formula sheet. There's a lot of formulas that we will invent in this class. One interesting thing about physics, actually, this is important, so I'm actually going to be on camera. One of the important and interesting things about physics is that physics is not just about taking an equation that we already have and plugging numbers into it and then solving for an answer. Any computer on Earth can take an equation that we already know and just plug numbers in and get an answer. You don't want to have a job that a computer can do a whole lot faster than you, because nobody's hiring if a computer can do the job faster than you can. What physics really is creating new equations out of the equations that we've already gotten from calculus, from experimentation. Physics is all about taking those equations and doing something new with them, combining them in new and interesting ways, creating entirely new equations to solve a problem. At the beginning of this course, we're not going to be doing a lot of that. We'll do some of that, actually. We will invent entirely new equations that only work on one particular problem. And that's actually what physics is about in many ways. Taking these equations, doing something completely new with them. Therefore, I'm going to give you a formula sheet that shows you all of the basic equations that just kind of always work, the ones that you can just plug things into. But on a test, you will frequently take those equations and use them to create entirely new equations to solve a problem that can only be solved with the equations that you create. And of course, we're going to do a lot of practice on that before I just throw you into it. So, as I just said, physics is more than just a bunch of equations. However, here's a bunch of equations that we're going to be using this semester. We've already used this. Acceleration is equal to change in velocity over change in time. We just figured this out, that the velocity is equal to the initial velocity plus your acceleration times the time. This equation right here looks a little bit complicated, but it's actually really easy. Your change in position is equal to 1/2 times your final velocity plus your initial velocity. Oh, sorry, your initial velocity plus your final velocity. When we have v naught, that putting a 0 next to it like that as a subscript, we pronounce that v naught. And the 0 just means not. But that also means, you can see down here, v naught is equal to the initial velocity, which we also sometimes call vi, for velocity initial. Now, different textbooks and different subjects will alternate between v naught and vi. Some physics textbooks use vi, some physics textbooks use v naught. Different engineering textbooks will use one or the other. And one thing I want to make sure that you can do after this semester is look at an equation and be able to translate it into something that you can understand. And so giving you multiple different kinds of subscripts is one way that I'm trying to train you to understand what all these mean. V naught, initial velocity. Vi, initial velocity. Likewise, if you just see a V, that's probably referring to your present or current velocity or your final velocity, whatever it is at the moment that you're looking at it. That's what V is, but we can also call that VF for V final. So what is this? It's our initial velocity plus our final velocity divided by 2 times t. Now, if we just look at the 1/2 times v naught plus v, well, this is our initial plus our final divided by 2. That's actually just your average velocity. If you have a constant acceleration, then your initial velocity plus your final velocity divided by 2 is your average velocity. That's how you find averages. You just add up the things and then divide by how many things you've got. So this is my average velocity right there times time. And average velocity times time is going to be your change in position. If my average velocity is 50 miles per hour and I'm driving for 3 hours, then that's 150 miles that I've driven. So average velocity times time is equal to your change in position. This fourth equation we just figured out on our own using calculus. We figured out why that works. This last one you can also figure out using some calculus and some algebra. So if you want to do that, you can. But our final velocity squared is equal to our initial velocity squared plus 2 times our acceleration times our change in position. It's actually some fun algebra to get there. So yeah, interesting equations that we've got. These are the kinds of things you can end up just plugging numbers into and getting something out. But it's a lot more fun when you have to do some smarter stuff to find your answer. For this, a car starts from rest and accelerates at a constant rate of 5 meters per second squared. I want you to choose the equations to use for each question. Once you've chosen an equation, everything else is a whole lot easier. So what is the velocity of the car after it's traveled 30 meters? How much time has elapsed as it's driven 30 meters? And calculate the average velocity over those 30 meters. For each of these, for now, just choose which equation you would use to solve each of these. Okay, I hope everyone has had a little bit of time to look at these. Let's talk about it. What is the velocity of the car after it has traveled 30 meters? Well, okay, what is the velocity of the car after it's done stuff? That means that we're looking for a final velocity. One of these needs to have the final velocity, and actually a bunch of them have final velocity. There's the final velocity, there's the final velocity. This one doesn't have final velocity. We do have final velocity there, and we have average velocity there, which doesn't really matter. Okay, so we're looking for the final velocity because we're looking for the velocity after the car has done something. What did it do? It traveled 30 meters. Okay, that's our delta x. Our 30 meters is how far it's traveled. So we need something with a delta x. Okay, we've got a delta x there, we've got a delta x there. And then, what else do we know about this? Oh, yeah, I'm seeing it in chat. We know that it started from rest. If it starts from rest, that means that the initial velocity has to be 0. Starting from rest means that you're not moving. Starting from it means that you are initially there. So that means initial velocity is 0. Okay, if initial velocity is 0, and we know our delta x, then, oh, we can use this one down there, this fourth equation. Our final velocity is what we're looking for. Our initial velocity, v0, is 0, plus 2 times a, which is 5 meters per second squared, times delta x, which is 30. You can, once you have the equation, then really that's it. I don't need to sit here and show you like plugging in numbers. At least I hope not. If I do, then email me and we can talk about it. But the most important thing is that we can figure out which equation to use. Now, how much time has elapsed? Okay, let's assume that we already solved A. How much time has elapsed? Well, if we've solved A, then we have the final velocity. We have the final velocity like that. The initial velocity is still 0. We still have an acceleration of 5 meters per second squared. We need to find the time. Looks like equation 1 would work just great for that. But also equation 2 would work just great for that. We've got our delta x, 30 meters. We've got our initial velocity, 0, our final velocity, which we solved in the first part. We're looking for time. So that would work really well. The third equation would also work really well to find the time. Delta x, got it, 30. V0, 0. 1/2 times 5 times t squared. We can use pretty much any equation at this point to find how much time has elapsed as long as it has a t in it. Of course, to find the average velocity, we should probably use this last equation there because it says average velocity. Comment from chat, equation 1 is simpler. And one thing that I want to teach you this semester, this is going to sound weird, I want to teach you to be lazy. A lot of people, most of you are engineers, and most of the rest of you are scientists. And engineers and scientists have a habit of overcomplicating things. You know this. I bet all of you know that at least the engineers and scientists out there know that you probably have a tendency to overthink things, overanalyze things. Sometimes that's good, sometimes that's bad. Sometimes it wastes your time. In this class, I want to teach you to be lazy and find the easiest way to every solution. And so for part B, how much time has elapsed, the easiest equation is clearly this first one. I can tell you that the exam will be more difficult than this. I'm trying to get everyone to a baseline here and then move on from this. We'll be doing more complicated stuff on the exam, but we'll talk about that before the exam actually happens. Here's the answers to that right there for the accelerating car. I tell you the numbers. and which equations you can use. I strongly recommend that you go back and do this on your own just to get a little bit of practice. You don't want the first time that you're practicing with this to be on the test. That is a recipe for failure. Practice well before the test. Here is some work that I did to show all that. So if you're having problems doing that on your own, you can go back and look at this and see how I solved all of those. Here is a very important point to make this whole semester about free fall acceleration. Free fall, that means that you're falling without anything acting on you. Freedom is all about not being acted upon by outside forces, I suppose. I don't know. So free fall is about falling without any outside forces acting on an object. If something is falling without outside things pushing on it, then it's in free fall. There's one exception to this, and it's the reason that the object is falling in the first place. That is gravity. Gravity will make things fall down. Welcome to first grade physics. Gravity pulls things down. It accelerates them down. It makes them speed up going downwards with a certain amount of acceleration. We define that acceleration to be g. Sometimes we call it little g because it's lowercase. Little g is a scalar, meaning it has no direction to it, and we just leave it as positive. G is just a scalar that is positive. The value of g is positive 9.8 meters per second squared. Now, in some parts of the world, it's actually closer to 9.81. In some parts, it's closer to 9.79, 9.83, things like that. It's about 9.8. And because it varies between 9.79 and 9.83, give or take, we're not going to have 3 sig figs on that. We're just going to use 2 sig figs on that because that's universally a good enough approximation. So g, the free fall acceleration, is positive 9.8 meters per second squared. However, an object accelerating due to gravity will accelerate at negative g, an acceleration of negative g, negative 9.8 meters per second squared in the y direction. Or we can say 9.8 meters per second squared down. Positive 9.8 down. The down makes it negative. This is another one of those vocabulary kinds of things. It's how we talk about it. Gravitational acceleration is a positive amount when we just list it as g, but we remember when we actually use it in a problem that it's going down and we had better attach a negative sign to it. Then we'll do some examples with that. So a ball thrown upwards might travel upwards, but it accelerates downwards the entire time. Now remember going back to those car examples where we talked about when things have positive acceleration and negative velocity, or negative acceleration and positive velocity. This is definitely one of those cases. Imagine, if you will, well actually, I can sit here and wave my arms around to show this. Imagine you have an object. You've got an object. You throw it up into the air. Throw it up like that. Well, it's got a positive velocity as it goes up. Positive velocity as it goes up. But as it goes up, it's slowing down. It's going up, but getting slower and slower and slower as it goes up. Therefore, it had a positive velocity, but because it was going slower and slower and slower, it was losing that velocity. Losing that velocity means that it had a negative acceleration. Acceleration is rate of change of velocity. So if you're losing your velocity as you go up, we're just talking about what happens when you go up. If you're losing your velocity as you go up, you have to have a negative acceleration, because negative acceleration means you're losing whatever you have up or gaining going down. So object goes up. It loses its velocity as it goes up. So it has a negative acceleration of, it turns out to be negative 9.8 meters per second squared, just as you'd expect because it's just gravity acting on it. Now, it gets to the top point and it stops and it turns around and it starts coming down. And as it comes down, it speeds up faster and faster. It starts off slow and then it speeds up as it comes down like that. So it has a negative velocity as it's coming down, but it's going faster and faster in the downward direction. So it has a negative velocity and a negative acceleration to build up more and more negative velocity as it comes down. Question to think about, what is the acceleration when it's at its highest point? I said that it goes to 0 velocity at its highest point. What is its acceleration at the highest point? I'm seeing it in chat. It's still negative 9.8 meters per second squared. At every point in this pen's motion, the acceleration is always negative 9.8 meters per second squared as it goes up and then down. A lot of people want to say that the acceleration at the topmost point is 0. And I totally get why they think that it would be a 0 acceleration up there. But let's think about what that would mean if that were true. If it had 0 acceleration at the top point in its motion, and it had 0 velocity in the top point in its motion, it would have no velocity, no speed, and no acceleration, meaning its speed was not changing. If something's acceleration went to 0 when it got to its highest point where its velocity is 0, its velocity would stop changing. That's literally what acceleration means, a changing velocity. Therefore, if it just got up there with a 0 acceleration, it would just hang there forever and never ever move. So if you ever threw something up into the air, as soon as it got to its highest point, it would just stop moving and just hover there forever with 0 velocity and 0 acceleration. Obviously, that's not the universe that we live in. We live in a universe where as you throw something up into the air, its velocity is always changing downward. Even when it's stopped up there, it's going to still want to be changing downward. So it'll go from a 0 velocity to a negative velocity just a nanosecond later. So it still had to have that acceleration as it started going down. That is free fall acceleration right there. Anytime you have something just going through the air like that, it could be a pen that you're throwing up. You could be throwing it across the room like that. You could have a cannon that fires something. As long as the only force acting on it is gravity, then you're going to have a downward velocity, a downward acceleration to it of 9.8 meters per second squared in the down direction. Here is an example problem, which is pretty much just what we did, but just with numbers now. I throw a ball into the air at 4 meters per second. How long, how much time until it comes back into my hand? And for now, we're just going to choose an equation. Let's see, I've got an initial velocity of 4 meters per second up. I assume that I throw the ball up into the air at 4 meters per second instead of down. So positive 4 meters per second, that's going to be my initial velocity. So I need an equation with an initial velocity. Oh wait, every single one of these has an initial velocity. That's V0. Okay, that does not narrow it down. How long, how much time until it comes back into my hand? Okay, so that means that I need an equation with a t in it, a time in it, because that's what I'm solving for. Well, this last equation does not have time in it, so we can say, okay, not that. Well, what else do we know about this? What is the delta x for this object? What is the change in position of this object from beginning to end? Well, presuming that I threw it from my hand and it comes back to my hand, then the change in position should be 0. Yep, I'm seeing it in chat. That's awesome. The change in position should be 0. So we need something with a change in position, a delta x, and we need something with a t in it. So it's going to be one of these two equations. Okay, well, let's look at the first one. 1/2 times v naught, okay, we know that, it's 4 meters per second, plus v, that's our final velocity. Do we know that just by looking at this? Not necessarily. Now, we'll talk about in the future how you can figure out that it's actually going to be just negative 4 meters per second. It should hit your hand at the same speed that you threw it out of your hand. But we don't technically know that yet. So I'm going to ignore this, the second equation, because we don't know what the final velocity is. You'll still get the right answer if you use that the final velocity is negative 4 meters per second. But we do definitely have everything that we need for this third equation. Delta x is 0, v naught is 4, t is what we're looking for. 1/2, that's just a number. A is negative 9.8 meters per second squared. Yeah, we've got to remember to plug that negative in there. And then we've got a t. So then it just becomes some algebra. 0 equals 4 times t plus 1/2 times negative 9.8 times t squared. Plug that into your calculator, do with a little bit of algebra, and you get that it comes back to your hand in less than 1 second. That's very quick. 4 meters per second is not very fast to throw something. That's like 9 miles per hour. So compare that to a baseball pitch, which can be a whole lot more miles per hour. This is a very slow throw. So yeah, it's going to hit your hand in less than a second.